So today we're going to finish up everything that the second derivative can tell us. All right, so we started yesterday. Okay, we learned a few new vocabulary words. What can we learn from the second derivative? So the new vocab.
Concave.
Okay, concavity or concave, different than a cavity like you get at the dentist, a concavity. All right, and what else? Point of inflection or inflection point. Okay, so those are the two takeaways yesterday with the second derivative can tell us. Second derivative can also tell us something else. That's what we're going to finish up today and really focus in on what we can learn from those graphs. All right, so you've seen this graph before, and we've asked the question, what does every maximum have in common?
It's its highest point in the local section.
Okay, I remember you gave almost the exact same answer. Okay, and that is true. Okay, it is its highest point locally. All right, what else does every max have in common?
Positive slope to the left, negative slope.
Okay, if we look at the first derivative is changing from positive values to negative values. Okay, what does every maximum have in common when you look at its second derivative?
Slope is 0.
That's the first derivative still. What does every maximum have in common in terms of its second derivative?
Decreasing and then increasing.
No? Okay. If this is a max right here, what kind of concavity does it have?
Down.
Negative concavity. If this is a max, what kind of concavity does it have?
Negative.
Okay, so what does every max have in common? Okay, it's sitting on top of negative concavity. Okay? So, two common features of every max. The first derivative changes, and it changes in such a way that we go from positive to negative. And the second derivative is totally negative. There's no changing of the second derivative in a max. Okay, so the first derivative, that's the first derivative test. The first derivative changes from plus numbers to minus numbers. Okay, that's always true. Okay, we change from plus to minus. But in terms of concavity, it's fully minus all the time. And so every max has those properties where the first derivative changes from plus to minus, but the second derivative is fully negative in that region, in that locality. Okay, and so then the same or something similar can be said about every min. The common feature of every min is that the first derivative is changing in a way that's going from negative to positive, but the concavity is fully what in that section?
Positive.
Fully positive in that section. And so every min here is going from negative to positive first derivatives, but sitting sitting at the bottom of a fully concave up section. So all of these have concave up sections. So either of those justifications are going to be valid when you give reasons why you think something is a minimum. All right, so if you are asked to justify, okay, find the max and justify your answer. Okay, you cannot say it's a max because it's the highest. Okay, that's like saying it's a max because it's a max. Okay, that doesn't work. Okay, it's not a solid enough reason. Your two choices for defenses are going to be, okay, it's a maximum because the first derivative does this, or it's a maximum because the second derivative does this. Those are your two options. You always defend it by one of the two types of derivatives, and the same thing would be for every minimum. So let's say what our minimum is. Our minimum has first derivative changing from negative to positive, or you could say the second derivative is fully or totally, oops, I can't spell, totally positive in that section, okay? Okay, so the next slide, slide 28, has that in formal language. The presence of a maximum can be detected or proven at a critical point And remember, what does it mean to be a critical point? It means that it came from a horizontal or a vertical tangent if the second derivative is fully negative there. Okay, so a max is connected to a second derivative that is negative. That's the connection. Sometimes people are like, max must be a plus. No. A maximum has negative concavity, whereas a minimum is connected to a second derivative that's positive. The minimum has positive concavity. So you can always tell. And you can make charts to tell that as well, just like we did with the first derivative. Okay, so to summarize, you take your endpoints, you take your critical points, and you could also perform the second derivative test to find out if they're maxes or mins. So you have two choices now. Both choices start with endpoints and critical points. You got to have those. Find your endpoints, find your critical points by doing horizontal and vertical tangents. Then, if you need to find maxes or mins, either make a chart to check the first derivative, see if it's changing in such a way, or make a chart to check the second derivative and see what kind of concavity it has. Either of those are totally valid. Do whatever is less work at the time for you. Okay, here's how you would defend it. And this is these if-then statements, so we practice our language. If, okay, tell me what this means. If f prime of c equals 0, what does that mean?
Slope.
Okay, and so what's happening when a slope is 0?
Vertical or horizontal?
Well, if it's equal to 0, what is it? Okay, that is a horizontal tangent. So if you have a horizontal tangent and the concavity is negative, then f has a local maximum. You can flip-flop that statement. F has a local maximum at C because there is a horizontal tangent and negative concavity. Okay, so horizontal tangent with negative concavity. That would make a max. But a horizontal tangent with positive concavity, like that, that's going to make a min. So if you could flip-flop that statement and make it not an if-then statement, but a because statement, f will have a local minimum at C because f prime of c equals 0, which made a and because the concavity was positive. You could also say that with a vertical tangent. It doesn't have to be horizontal. It could be undefined as well. Okay, because it's a cusp or because it's, okay, a corner or something like that. All right, so let's use the second derivative test to find the extreme values. All right, so make sure you kind of cover all the pieces. First step, endpoints. All right, this one has none because I know what cubics look like, and this cubic doesn't have any endpoints. Critical points. I move on to find the f prime values, which is going to be 3x squared minus 6. I set that equal to 0. What solutions do you get when you set 3x squared minus 6 equals to 0? Okay, plus or minus the square root of 2. And then I also take 3x squared minus 6 and I set it equal to 1 over 0. And what additional solutions, if any, do you get? None. All right, those are my critical points. So I know now that I have horizontal tangents. That's what I've gotten so far, that here are the horizontal tangents. And at this point, you have a choice. Do you want to check the first derivative and check for a plus minus or a minus to plus change? That would be fine. But I'm here to tell you that you can also check the second derivative, and you can check the concavity instead. So if I'm going to check the concavity, I would need f double prime. F double prime of this is going to be 6x. And then I just check both square root 2 and negative square root 2. if I plug in square root 2 into the concavity, what kind of a number do I get? I get positive. So if the square root of 2 is both a horizontal tangent and positive concavity, what does that mean? Very good. Can you picture that? It has both a horizontal tangent and positive concavity, which is like the U sitting up there like that. So it has to be a minimum. Okay, so that's our conclusion. X equals rad 2 is a local min. How do I know it's not an absolute? Because I know what a cubic looks like, and I know that cubics go on forever. When I check the concavity of negative rad 2, I'm going to get a negative number. That means it has both a horizontal tangent and negative concavity, and so I can conclude from that that x equals negative rad 2 is a local max because it has both a horizontal tangent and negative concavity at the same time. So hopefully you can picture that. Horizontal tangent, negative concavity, that means that point is a maximum. So this is another way to prove maxes or mins. You can either do a plus minus chart or you can check concavity, either one. Any questions so far? All right, then let us conclude with kind of a whole summative thing. More often than not, you will not be looking at the function itself. Okay? So just imagine you were looking at the function. Okay? That would be sort of an Algebra 1 level question. If you were looking at this function and I said, Algebra 1 student, can you find the minimum? Almost all, they probably would say, oh yeah, right here, those are the minimums, because they can just look at it and see it. Okay? More often than not, you are going to be told you're not looking at the function, you're looking at the derivative of the function. Okay? So let's practice doing that. This is a derivative. This is like in your physics classes when you're looking at the graph of a velocity curve. You are looking at the graph of a derivative right now. From the derivative, you can tell where the max and the mins of the original function are going to be if you know how to read it. Okay? All right, so tell me what's true about every maximum. It might have a horizontal tangent or a vertical tangent. Okay, if it has a horizontal tangent, its derivative value is what? 0. Okay, if it has a vertical tangent, its derivative value is undefined, which looks like an asymptote. Okay, that's how what undefined looks like, an asymptote. All right, do you see any places where the derivative values, if this is the derivative graph, are 0? Okay, you see 3 of them, right? Okay. All right, so let's go to this next one. Next slide. Label those 3 spots. Okay, so you've got this one, has a horizontal tangent, this one, that one. Those are the 3 horizontal tangents. Is that enough to know if they're maxes or mins? No. All you know is that they have horizontal tangents. Okay? Now, to know if they're maxes or mins, all we have to know is what the change is happening around them. Okay? What kind of change is going on around those horizontal tangents? So let's look at this one right here in that neighborhood. It is changing as that function travels from quadrant 2 to quadrant 3. What kind of numbers are in quadrant 2? Positive numbers when you're looking at their y values. And what kind of numbers are quadrant 3? Negative. So this is changing from positive to negative. So then what does that mean is happening at that very number? Okay, that is a maximum. When the first derivative changes from positive to negative, you have identified a max. So your argument would be, I predict that the original function will have a maximum at x equals -2 because it has a horizontal tangent there and because the derivative values are changing from positive to negative. All right, let's look at the last one. Okay, there's a horizontal tangent going on at +2, but it's going on in such a way that it's going from negative values to positive values. And so you would cast your argument that I'm going to argue that the function has a what? Minimum. Where? At +2. Why?
Because its derivative changes from negative to positive.
And it has a horizontal tangent. Okay? So yes, it has a what? A min. Where? At +2. Why? Because there's a horizontal tangent there, since the derivative is equal to 0, and the derivative is changing from negative to positive. All right, so let's look at this last one in the center here. We know it has a horizontal tangent because the derivative was equal to 0 at that point. But what's going on before and after? Negative to negative. So there's no change. Okay, there's absolutely no change going on here. So that is not a maximum. It is not a minimum. Well, what is it then? It's a point of inflection, right? Okay. All right, so that answers these questions here. Find the x coordinates where there is a max or a min. We just did that. All right, so then let's look at the bottom set of questions. Also, find the intervals on which the function is rising or increasing, going up, or falling or decreasing, going down, okay? And so that's going to be happening between all of the horizontal tangents. Okay, between all the horizontal tangents, what do I have? So sometimes it's helpful to set it up like this, if you'd like. Between all of the horizontal tangents. And then just make some pluses and minuses to help you out. So this would be a plus because it was above the x-axis. This is a minus because it's below the x-axis, followed by a second minus because it's below the x-axis and changing to a plus. And so then we can identify when the function is rising. The function is rising on the intervals x less than -2 and x greater than 2 because the first derivative is positive. And the function is falling or decreasing from -2 to 0 and 0 to 2 because the derivative is negative. Are there any questions on that? All right, we've already talked about point of inflection, but let's talk a little bit more about that. Okay, we've identified, or we think there's going to be a point of inflection right here because it had a horizontal tangent, but it didn't have a change. It was minus changing to minus. Okay, are there any other points of inflection? Okay, well, there's two other points that are important about this graph. We've already talked about these three, but are there other important spots? Okay, yeah. And the other important spots are down here. Okay, this is, remember, we're looking at a first derivative graph, but what do the max and mins of the first derivative graph mean? Well, then those are important for the second derivative. Those values, because they are maxes and mins of the first derivative, tell us something about the second derivative. Those three things represent points of inflection because it's where the direction of the derivative slope changes. I've got a whole direction, this whole thing. Okay, that is the slope of the derivative. Okay, I want you to look at it in English. This is the slope of the derivative. Okay, I'm looking at the derivative and I'm looking at the slope of the derivative. But what word is synonymous to slope? It's derivative. So I could change this to be the derivative of the derivative. And that means the second derivative. Okay, so the slope of the derivative is its second derivative. So this is all negative because it's all decreasing. This is also negative because it's decreasing. Those negative sections represent negative concavity. And then we've got some positive sections. Got a positive section here and here. Those positively sloped sections represent positive concavity. So if we put all that together, you would have something like this. X is less than, and that's the square root of 2. And then from the square root of 2 to 0, and then from 0 to the square root of 2 again, positive, sorry, one of them was negative, that was, and then greater than the square root of 2. And in the second derivative, we have a minus changing to a plus, changing back to a minus, changing to a plus. This is the second derivative now. So every time the first derivative changes, you have maxes and mins. Every time the second derivative changes, you have points of inflection. So I have 3 points of inflection. I have a point of inflection at -2. I have a point of inflection at 0. And I have a point of inflection at 2, at rad 2. And then I have 2 concave down sections, and I have 2 concave up sections. This is all from reading the graph of the first derivative. I don't even know what the regular function looks like, but I can tell you a whole lot about it just from being able to read this. Okay. I'm going to try it with a different looking graph this time, unless there's questions on this. Okay, this is our last graph.
Can we
Yeah.
figure out what kind of concavity the original has? Because
Yes, the original graph has negative concavity, followed by positive concavity, followed by negative concavity, followed by positive concavity.
okay, just trying to picture that in my head.
All right, let's try this. Okay, here is a graph, and you're told again it represents the first derivative. All right, so the first thing you want to do is look for places where there might be horizontal tangents. Okay, all right, so based on that, tell me a letter that you think there might be a horizontal tangent on. Okay, Alex, do you want to try? Just a horizontal tangent. Good. A has a horizontal tangent. Great. Okay. All right, Julie, you want to try one? Is there any other horizontal tangents? C has a horizontal tangent. Good. Okay. Okay, is there any other ones? Catherine, any horizontal tangents? E does. Okay, anybody else? G is a horizontal tangent as well. Okay, great. All right, are there any other tangents? I'm just going to circle so I have the letter included. A, C, E, and G. Any other tangents? Okay, those are all three, or all four horizontal. All right, any vertical tangents?
Yeah.
YF. Okay, it's undefined. Okay, F is undefined. And when F is undefined, undefined means it has a vertical tangent. And so, yes, you got to pick up on F then being a vertical tangent. So now, if you're going to identify maxes and mins, I think it's easiest to make this into an inequality chart and throw some pluses and minuses on it. You can do it your own way, but this is how I'm going to do it. I'm going to say, all right, everything less than A, And for everything less than a, I have a minus sign because I'm below the x-axis. Then I'm going to go from a to b, a to c, which is where my next horizontal tangent is, and everything between a and c is above the x-axis. And then I'm going to go from c to e, and everything between c and e is below the x-axis. Then I'm going to go from e to f. Not all the way from e to g, but I have to stop at f because f had a vertical tangent. And between e and f, I'm above the x-axis. And then I'm going to go from f to g. And in that section, I'm still above the x-axis. So notice it was from a plus and it stayed plus. But I still have a vertical tangent there. Okay, still got something going on. Maybe it's a cusp. Maybe it's a corner, something going on. And then we have anything greater than g, and that's a minus. So once you have that set up, you can identify the 1, 2, 3 sections that are decreasing. So my decreasing sections would be here, here, and here. And so we would say the function is doing what? Decreasing. Where? On those intervals. Why? Because the first derivative is negative. And then we have 3 increasing intervals. And again, so the function will be increasing on blank, 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 those 3 intervals, okay, because the first derivative is positive. And then you can identify what kind of maxes and mins that you have going on. Okay, first derivative, you say, all right, decreasing to increasing, that's a min. Increasing to decreasing, max. Decreasing back to increasing again, min. A double increasing section, that's neither a max or a min. What do you think it's going to be? Okay, and we'll get to that on the our last slide. And then increasing to decreasing, we have another max. So you can identify that there are 2 mins and 2 maxes. Yeah.
Can you remind me again why something like is increasing of horizontal tangent?
Okay, because the definition of a horizontal tangent is the first derivative is equal to 0.
Oh, right.
And we are looking at the first derivative, and the first derivative is not equal to 0 at b. All right, but what you're thinking, b is important. Okay, so this is our last slide. Okay, b is an important number. So what is b going to represent? So now we have to think about, okay, now I have to think in terms of the maxes and the mins of this, and those are going to represent points of inflection to me. And so I'm going to have b is going to be important, d is going to be important, and f is going to be important again because it is still a broken spot. So I'm going to set up intervals around those 3 things. I'm going to have less than b. I'm going to have from b to d. I'm going to have from d to f. And then I'm going to have things that are greater than f. And what I'm looking at now is what's going on between those sections. Okay, just remember we've got an asymptote here. We've got some kind of broken discontinuity going on there. So let's start between B and D. Let's start between this region right here. And remember, now you're looking, not is it above the x-axis, not is it below the x-axis, but let's look at what kind of slope it has. All right, so what kind of slope connects B to D? Negative slope. And if that has negative slope, if the slope of the derivative is negative, or the derivative of the derivative is negative, that means the second derivative is negative, which means I have a whole section that's behaving in what way? Concave down. Very good. So this is concave down. Okay, if we want to look at the section between that's preceding that whole section there has positive slope. which means this whole graph is concave, that whole section is concave up. Between D and F, to that brokenness, we have another positive section, which means it's concave up. And then from the whole thing, from F on through the rest of the graph, we have a negatively sloped section, which means it's concave down. Then I have 3 points of inflection. Every time it changed, concavity, that's defined as a point of inflection. All right, any questions about that? So you're going to have graphs to read where you're looking at the first derivative, not the original graph. And then next we'll get to, can you try and draw the original graph from the information that you have? But that'll be another day.
Is that tomorrow?
Yeah,
That's all.
and put it all together. So let me save this.